Now, I also introduced earlier as well this volumetric efficiency, which is mass of air induced into the cylinder divided by mass that would occupy the displaced volume, which is a very important parameter for us to decide the performance of the intake system of an engine. In simple speaking, it is mass per air per cycle divided by the density of the air under intake conditions, environmental conditions or ambient conditions, into the VD, that is the displaced volume. So this is the mass that could occupy under standard conditions by the displaced volume. And this is the mass actually has been induced into the system. Again, when it comes to representation of parameters, it is very important to represent the numbers or represent these variables in the form of measurable quantities. And as I said earlier, the mass per cycle is not a measurable quantity. What we could do is the mass flow rate. So as we have converted work into power earlier, same concept would be used to convert this mass per cycle into mass flow rate into the engine. Accordingly, the volumetric efficiency could be represented like this. N is the speed in revolutions a second. NR indicates will be 1 or 2 depending upon whether it is a 2-stroke engine or 4-stroke engine. And MA dot is something that we can measure from the intake air sensor. If you carefully look at the things that we induce into cylinders during the intake process, what we see is not only air. In spark ignition engines, we introduce fuel into the intake system. So there is fuel in the intake system during induction process. And also, the exhaust process is not 100% efficient. That means there is some amount of exhaust gases left over in the cylinder at the end of the exhaust process. Therefore, the incoming air is mixed with not only the fuel, but also the burn gases from the previous cycle. So that burn gases from the previous cycle is called the residual gases. So we could represent the fraction of residual gases or residual mass fraction as the ratio of residual gases to the total mass of the cylinder. So total mass of the cylinder. And MR is the residual masses in kilograms. M is the total in-cylinder mass that has residual gases, air, as well as fuel. And if FOA is air-fuel ratio and V1 is the volume at the bottom dead center and V2 is volume at the top dead center, and RC is the compression ratio, we can obtain some relationship for volumetric efficiency with more parameters into it. For example, total mass, as we just said, is MR plus MA plus MF. XR is MR over M. F over A is fuel air ratio is MF over MA. And if you substitute values for MR and MF using these two relationships in here, then this will be modified to XRM plus MA. So this is the residual mass. So the residual mass fraction into total mass. And the fuel, mass of fuel, is represented in the form of mass of air using air-fuel ratio, the fuel-air ratio. If you take M to one side and MA to other side, then we can get a relationship for MA, which is M into 1 minus XR, that is residual mass fraction, divided by 1 plus F over A, that is fuel-air ratio. And similarly, compression ratio is the maximum volume to minimum volume ratio. And of course, the minimum volume is maximum volume minus the displaced volume. So if you obtain a relationship for displaced volume, then we could represent it in the form of as a function of maximum volume and the compression ratio. as you can see here. So now we can substitute these values into the equation for volumetric efficiency that we looked at earlier. And this is what we obtained for MA. And this, if you want to represent in the form of MA dot, that is mass flow, air flow rate, then of course this has to be mass flow rate to the system. So you can replace this MA dot with this. Similarly, the displaced volume could be replaced with this blue relationship. And if you plug in this and simplify it, you will get a relationship like this. So the volumetric efficiency depends on the total mass flow rate into the system, residual mass fraction, compression ratio, maximum volume, air-fuel ratio, and so forth. So these are some of this elaborated formula, rather than just mass induced into the system divided by mass could have been induced. So we can incorporate some more parameters, and that indicates that the volumetric efficiency not only dependent on the restrictors in the intake system, for example, in petrol engines, but also certain parameters like residual gas fraction or residual mass fraction, compression ratio, air-fuel ratio, etc. Next, the specific fuel consumption. Specific fuel consumption is the fuel consumption per unit power, amount of fuel required to, so the fuel flow rate required to produce one unit of power. So as said earlier, depending upon what power you use, you can work out what type of specific fuel consumption that you're looking for. For example, if you use brake power, that will be brake specific fuel consumption. If you use indicated power, that could be indicated specific fuel consumption. Now, this is an interesting diagram. You can see we call it is engine performance maps. We talk more about this with time, but just want to introduce it here as we talk about specific fuel consumptions. So engine performance maps are drawn considering the engine speed and the brake mean effective pressure or the brake torque. They are directly related. We plot the brake specific fuel consumption at different brake mean effective pressures or brake torques and different speeds. So what you see is something like this. So the top curve indicates the wide open throttle condition situation, and the partly load conditions are indicated here. So you can see this number. This number indicates brake specific fuel consumption. Brake specific fuel consumption. Now in this case, it is 280 here, 300 here, 335 here, 400 here. So the brake specific fuel consumption increases over here. So this is the contour map, and the smallest minimum value is here, and the largest value here. So it's like a valley in a mountain. So this is the peak goes here, and this is the shallowmost points. And as you can see, brake specific fuel consumption could be minimum if the engine is operated under different load conditions, different torques. But if you can maintain the speed like this. So this graph is for petrol engines or spark ignition engines. The same type of graphs can be drawn. The contour maps can be produced for spark compression ignition engines as well. And if you, for example, if you look at a particular operating point, like piston speed is about 8 meters a second. This is mean piston speed rather. And brake power, that brake mean effective pressure that you are taking out from the engine is little less than 6. Then this gasoline engine consumes about 300 grams of fuel to produce 1 kilowatt hour. On the other hand, in this compression ignition engines, at the same piston speed, 8, and about the same brake mean effective pressure, little less than 6, you can see this compression ignition engine consumes about 275 grams to produce 1 kilowatt hour of energy. So that means it is clearly indicated that compression ignition engines consume less fuel compared to the same operation level of spark ignition engines. In this case, this is 300 grams and this is 275 grams. Therefore, this clearly indicates that compression ignition engines are more efficient than the spark ignition engines. The reason is basically very simple. As we said earlier, the compression ratio of diesel engines are much more than the compression ratio of practical spark ignition engines. And the compression ratio is directly related to the fuel conversion or the thermal efficiency. Therefore, because of this high compression ratio, you could see better performance in terms of thermal efficiency or specific fuel consumption in compression ignition engines. So the fuel conversion efficiency, which is also known as the thermal efficiency, gives us an indication of how good the engine is in converting the chemical energy in the fuel to useful work. So that is directly computed by dividing the work produced per cycle by the amount of energy released by the fuel during that cycle. So amount of energy released by the fuel per cycle can be calculated if you know the mass of fuel burned during this cycle and the calorific value of the fuel. And work, of course, we looked at earlier, can be calculated using a PV diagram if it is indicated work that you are looking at. So the ratio between work and the energy released by the fuel is the thermal efficiency of the system, which indicates how good the engine is in converting the chemical energy into work. Now, again, when you look at MF and WC, these are per cycle quantities which are very difficult to estimate or calculate. Accordingly, we prefer to have them in the form of rate of change of work or rate of change of fuel. So that is power and mass flow rate of fuel. So you can convert this WC and NF into flow rates and power by using the same conversion that we looked at earlier. And accordingly, we can represent the thermal efficiency like this. Now, this quantity that we looked at earlier is MF dot divided by P is the specific fuel consumption. So thermal efficiency could be represented as 1 over specific fuel consumption into the calorific value of the fuel. 1 over specific fuel consumption into the calorific value of the fuel. Now, the brake specific fuel consumption basically highly dependent on the engine size. Larger engines have relatively smaller brake specific fuel consumption that we can discuss in detail as we go on. We are talking about brake specific fuel consumption. So if the consumption is low, always it is good. And this chart shows us the brake specific fuel consumption, variation of brake specific fuel consumption with the displacement of the engine, that is VD, displacement of the engine. We can see there's a rapid decrease of the brake specific fuel consumption when you increase the displacement of an engine. So there are many reasons for that, but one simple, straightforward reason is, as I mentioned earlier, if you look at the cylinder surface area to cylinder volume ratio, we can see surface area to volume ratio reduces with the increase of value of R, that is the radius of the cylinder. So that is radius of the cylinder, which is twice radius of cylinder is the bore. So when the bore is increased, surface to volume ratio is reduced. And when the surface to volume ratio is reduced, surface area is reduced, we know that the heat transfer is reduced. So higher bore diameter, smaller the surface volume to ratio, thus we could expect comparatively lesser heat losses. So that is one of the reasons for having low brake specific fuel consumption in large engines, but there are many other things that affect on that, which we discuss in detail as we go on. This graph shows us the variation of brake specific fuel consumption with the engine speed. So you can see at low speeds, brake specific fuel consumption is high, as well as high speeds, brake specific fuel consumption is high. The reasons are at high speeds, the friction increases, the viscous friction increases, therefore the fuel consumption increases. And at low speeds, the engines operate at slower, therefore there is more time for heat to escape from the engine. So heat transfer is more because the gases are in touch with the walls of the cylinder, more time than when the engine runs at higher speeds. Accordingly, the heat transfer is more at low speeds than high speeds. Accordingly, we could exhibit this kind of variation. More brake specific fuel consumption at low speeds as well as high speeds. So that means there is a speed at which we could get the best brake specific fuel consumption. And also brake specific fuel consumption reduces with the increase of compression ratio for the obvious reasons. If the compression ratio is increased, the thermal efficiency is increased. Accordingly, brake specific fuel consumption or indicate specific fuel consumption should go down. Now, this table summarizes all the formula that we have derived and discussed. So it's a summary of what we have just looked at. And this table gives us an idea about the real practical values of some of the parameters that we discussed. For example, if you look at spark ignition engines, small motorcycle engines, they can be two-stroke. Two-stroke motorbicycle engines are banned in Sri Lanka at the moment. You can't import, but still we find two-stroke engines on the roads. The compression ratio could be in the range of 7 to 11. The stroke to bore ratio, the maximum speed, rated maximum speed, rated maximum brake mean effective pressure. It's about 5 to 12 bars, not in kilopascals, C8 is in bars. That means 500 to 1200 kilopascals. And the power per unit volume, weight to power ratio, and the best brake specific fuel consumption. So you can compare, you can get an understanding about the real values of these parameters that we discussed. At the same time, you can compare the engines of different sizes. For example, if it is a passenger car, so these are the values. Passenger car naturally aspirated, NA means naturally aspirated. And if it is turbocharged and intercooled system, you can see we can increase the power per unit volume drastically. And also we can reduce the weight to power ratio. And likewise, you can compare the performance. If it is a diesel engine, it's like this. These are the values. And naturally aspirated and turbocharged. And if it is large marine engines, massive engines, you can have an idea about these values. So I'm not going to go through all the numbers. So you take time and go through this table and get an understanding about the real values of practical engines. So this is what we earlier discussed as a summary. So indicated mean effective pressure peaks at a certain speed and comes down after when the speed is increased due to reduction of volumetric efficiency. And the brake mean effective pressure also peaks at a certain speed and comes down after that, just because the frictional effects increases with the speed as well as the drop of volumetric efficiency. And the variation of brake power, indicated power, friction mean effective pressure, friction power also indicated here. And so this is the speed versus volumetric efficiency. Speed is given in terms of mean piston speed. So the volumetric efficiency in compression ignition engines are always higher than spark ignition engines because we do not throttle compression ignition engines. And at the same time, you can see at high speeds as well as low speeds, the volumetric efficiency drops down. At high speeds, of course, the flow dynamics makes it to drop down, and at low speeds, the heat transfer makes it to reduction of the volumetric efficiency. In addition, mechanical efficiency drops with the speed because the friction increases. Brake specific fuel consumption increases with the speed due to the increase of friction. Variation of indicated specific fuel consumption against the speed is also shown here. This for the particular engine described over here. And this slide compares some of these values that we just looked at for certain commercial engines. Again, just for your information, I have included this just to get an idea about those values of different engines. And this is the performance versus the speed. Again, brake specific fuel consumption. So it peaks at low speeds and high speeds. And there's a minimum value that you can find, usually around 1,500 RPM. And then the brake power, again, increases with the speed, but it finds a peak. And after that, it drastically reduces. The torque also finds the peak at a certain speed and drops down as the speed is increased. The reasons we just discussed, and we can see the torque, you could get the maximum torque of an engine somewhere here, the maximum power of the engine somewhere here. Usually, the engines operate at 1,500 RPM, gives us the best fuel consumption. That is the right operating point as far as the speed is concerned. But the vehicles we operate under wide range of operating speeds. Like sometimes we run vehicles at 10 kilometers an hour. Sometimes we run vehicles at 100 kilometers an hour. So the speed changes according to the road conditions, driver requirements, traffic situation, etc., etc. So the vehicles need to be operated at wide range of speeds. But when it comes to the prime move of these vehicles, the internal combustion engines should operate at a near constant speed. Accordingly, we use something called gearbox in the engine to make sure that, irrespective of the vehicle speed, the engines are operated in a narrow band of speeds, like in this band, so that we get the best efficiency as far as the fuel consumption is concerned.